Hey, it's Mr. Salatano, and this video is going to explain how to convert from moles to particles and from particles back to moles. So to start with, we've already mentioned how a mole is just another word sort of like a dozen, and a mole is 6.02 times 10 to the 23rd representative particles. But it's really important that we talk about what a representative particle is. It's technically the species present, so usually the atoms, molecules, or formula units. It's the way that we describe the chemical we're working with, and it makes a big difference, which we're going to talk about in a little bit. So for example, most elements, right, in elemental form are composed of just atoms. But 7 of them that we've talked about in the past are molecules because they consist of 2 bonded together. So for example, O2 and H2, we can kind of see them over here a little bit. Cl2, Br2, all of those diatomics, we call them diatomics because it's a molecule made of 2 atoms bonded together. That's very different than atoms of hydrogen. So a molecule of hydrogen, which has 2 hydrogens, is very different from an atom of hydrogen. So how do we know what kind of representative particle to use? For example, copper, which just exists as atoms of copper, we would use atoms for that. Copper naturally exists as separate atoms. Nitrogen, though, naturally exists as N2. It's one of our diatomics, so we would call that a molecule. Water, which is made of hydrogen and oxygen, 2 nonmetals, so in other words a molecular or covalent compound, we would consider a molecule. Whenever you have an ionic compound like sodium chloride, Na and Cl being a metal and a nonmetal, you're going to call that a formula unit. Now if we look down below, we can kind of visualize this. So here we have our copper atoms. Again, they're just kind of separate spheres that make up copper. And then here we have our molecule of nitrogen, which consists of a couple of atoms bonded together, so we have to refer to that as a molecule. Here we have water, which consists of all nonmetals, and our formula unit of salt, which we'll talk about in another unit, for NaCl, is actually a smaller lowest ratio piece of a larger overall crystal lattice that we'll talk about later. So a formula unit is very different than a molecule. For now, we just need to know that a metal and a nonmetal combine to make a formula unit. It's a very different particle than a molecule itself. Okay, so why does it matter? Here's an example of why it matters. On the right, we have a dozen H2O molecules. Right, so right over here we have a dozen H2O molecules. How many molecules do we have? Well, we have 12, right? I mean, a dozen we know is 12. How many dozen hydrogens do we have? So don't jump too quickly to answer. First we have to think. We have 12 water molecules, and each water molecule has 2 hydrogens attached to it, right? So each of these has 2. The white part is the hydrogen atom attached. So if we were to count them, we'd have 1, 2, 3, 4. We would have 24 total because there's 2 per every water molecule, and we have 12 water molecules, so we double it. So because we have 24 atoms of hydrogen, we can say that we have 2 dozen atoms of hydrogen. So when we have 1 dozen water molecules, shown on the right here, we have 2 dozen hydrogen atoms. We have double the number of the white particles compared to the overall chemical. How many dozen oxygen atoms do we have? Well, the oxygen is the red, so there's only 1 oxygen per every water molecule. So if we have a dozen water molecules, we have a dozen oxygen atoms. So 1 dozen there. The mole works the same way. So if we have a mole of H2O, that means that we have 2 moles of hydrogen atoms, just like we had 2 dozen hydrogen atoms, and 1 mole of oxygen atoms. So it's very important when you say molecule or atom, which one you mean, because 1 mole of water molecules contains 2 moles of hydrogen atoms and 1 mole of oxygen atoms. So the overall structure when they were bonded together was a molecule, but the separate atoms are atoms, and so that's why we have to really designate which one we're using. But okay, so let's get to the heart of this. Let's try some practice with how to convert this. How many atoms of copper are in 4.5 moles of copper? So first thing, always start with the given. We've got 4.5 moles of copper, and we're going to multiply by our fraction to do our dimensional analysis. The unit on bottom is going to have to be moles because we're trying to cancel. And we always use 1 mole. Just to keep it simple, we're going to always use 1 mole somewhere in our conversion factor or our fraction. Now, the question is, on top, whatever we put on top of this fraction has to be somehow equal to whatever we put on bottom. So, how many atoms are there in 1 mole? Well, in this case, we just use Avogadro's number. So, Avogadro's number is 6.02 times 10 to the 23rd. This is how many is in a mole of anything. So anytime you're using particles, such as atoms, formula units, molecules, or ions, for example, we're going to use this number. This is not a mass. We use the periodic table for a mass. This is for particles. So atoms are particles, so we're using this number. And then we know if we did it correctly because our moles cancel, and we are good there. So we would multiply across the top and divide by the bottom, technically, and we would get this answer. So let's do the reverse. How many moles of copper are in 3.311 times 10 to the 24th atoms of copper? So we start with our given atoms, this many atoms of copper. We're going to multiply by our fraction. And in this case, our 1 mole is actually going to be on top, which we'll get to in a second. Atoms have to be on bottom. But because atoms are a particle, we're going to again use that 6.02 times 10 to the 23rd atoms, in this case of copper. Going to put our 1 mole on top. Now this type is a little bit different, so you have to be very cautious. When we actually go to put this math in the calculator, we have to use parentheses around the 6.02 times 10 to the 23rd. Why is that? Well, if you don't use parentheses, your calculator will see this as 3.311 times 10 to the 24th divided by 6.02, and the whole thing times 10 to the 23rd, rather than this big whole number divided by this whole number. So it's really important that you put it in parentheses when you're dividing. If you're having trouble remembering, just put it in parentheses every time. But okay, so we go to divide and we get this proper answer. You will know if you didn't do it correctly because you'd get an answer like this. Anything times 10 to the 40-something power is going to be way too big a number. Times 10 to the 23rd is already a huge number we're dealing with, right? Times 10 to the 46th power in this case, for example, way too big. So if something went wrong, always double check in your calculator if you get something times 10 to the 40th power. Okay, switching it up a little bit, how many atoms of hydrogen are in 2 moles of water? So notice how they said how many atoms, and we know that water's representative particle for a full H2O is actually molecules, right? So we have to be really careful with this one. There's a couple different ways you could do it. You could start with 2 moles of water, and then of course we'd have to put our 1 mole on bottom to cancel. The 1 mole's got to be in there somewhere, and we're trying to cancel most, so it's got to be on bottom. And on top, because we're dealing with particles, we would use 6.02 times 10 to the 23rd. Notice I put molecules of H2O here. So when we solve this, we would get this answer. But this is not the final answer. We just found how many molecules of H2O we have. So the question says how many atoms of hydrogen. It's very different, right? So there's a couple different ways we could do it. One way is we could say, all right, well, we know that for every molecule of water, right, H2O, there's 2 atoms of hydrogen in there, so we could just double our answer. And that would give us the correct answer is actually this many hydrogen atoms total, because we know there's 2 H's for every water molecule. The other thing that we could do is we could know off the bat that there are 2 moles of hydrogen, right, 2 moles of H in every 1 mole of H2O. So if the problem starts with 2 moles of water, we can say, okay, that's the same as 4 moles of hydrogen atoms, 4 moles of H. And we could go to cancel that out, use our 1 mole of H on bottom, and our 6.02 times 10 to the 23rd H atoms. So now we're in atoms using the different representative particle. And those would cancel. So that is it essentially. You would get the same answer that way. 2 different ways to do this problem. So that's it for mole to particle conversion and particles to moles. Thanks for watching, and remember, chemistry is everywhere.